The James Webb Space Telescope is revealing the universe like never before.
And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain.
Again, James Webb astonished us with an incredible find. Dubbed as a sentinel that would expose secrets from the deepest locations in space, the Premier Observatory may have just recorded one of its most spectacular observations to date, the detection of what appear to be artificial lights from a distant world, 7 trillion miles from Earth. This remarkable finding then sparked curiosity about the possibility of extraterrestrial life. But after all, has James Webb really found life beyond Earth? Join us as we dig deep into Webb's stunning discovery and what it could mean for future space exploration and our understanding of life beyond Earth. In January 1992, 2 radio astronomers, Alexander Wolszczan and Dale Frail, announced a finding that would forever change humanity's perspective on the universe. Wolszczan was studying pulsars, a type of rapidly spinning star known for its unique emissions. However, during his observations, he noticed an interference that wasn't typical of pulsar activity. Intrigued, he dug deeper to determine what could be blocking his view and ultimately made a groundbreaking discovery: 2 planets orbiting the star. Frail, a fellow astronomer, confirmed the data, and together they made an announcement that shook the astronomical community and beyond. They had discovered the first ever confirmed planets orbiting a star beyond our own sun. These exoplanets marked the first definitive proof that other planetary systems existed, affirming the possibility that the solar system was not the only one in the cosmos. This revelation fueled a surge of interest among astronomers, spurring a collective mission to uncover more exoplanets and learn about the diversity of worlds that may exist. The search for exoplanets has advanced rapidly, thanks in part to powerful tools like NASA's Kepler Space Telescope. Launched in 2009, Kepler represented a leap forward, specifically designed to detect exoplanets by measuring small dips in starlight as planets crossed in front of their host stars. This innovative method, known as the transit method, proved remarkably successful. Over the years, Kepler and subsequent missions have identified over 5,000 exoplanets, revealing a kaleidoscopic array of planetary types and compositions, some of which bear striking resemblances to Earth. Each discovery has answered fundamental questions about planetary formation, yet they have also led to even deeper, more profound mysteries. What types of planets can harbor life? Could our universe be filled with planets that sustain life in ways we have yet to imagine? In response to these lingering questions, a new generation of space telescopes has been launched to push the boundaries of what we know about exoplanets. Among these, the James Webb Space Telescope stands out as the most powerful, often seen as the successor to the Hubble Space Telescope. Webb's design boasts 100 times the power of Hubble and an orbital position 1.5 million kilometers from Earth, around the second Lagrange point. This strategic placement allows the telescope to remain free from interference caused by the Sun, Earth, and Moon, maintaining an ultra-cool operating temperature near -225 degrees Celsius. This cold environment is essential for its primary observation method, infrared imaging. Infrared light enables James Webb to penetrate dense clouds of gas and dust, revealing young stars and planets that are otherwise obscured in visible light. One of Webb's main goals is to observe the earliest stages of planetary formation. As clouds of gas and dust coalesce to form stars, these young protostars are often surrounded by swirling disks of material. Over millions of years, planets may form from this disk, orbiting their parent star in systems similar to our solar system. These early formation stages are difficult to observe because visible light cannot penetrate the thick dust surrounding young stars. However, Webb's infrared capabilities allow it to see through this dust, offering unprecedented glimpses into the dynamics of planetary formation. In the words of Dr. Jane Rigby, a project scientist for James Webb, "We build space telescopes because they can take sharper pictures. Earth's atmosphere distorts what we're trying to see, especially in the infrared range. So to study this light, we need to go into space. By escaping atmospheric interference, the telescope can examine the structures and compositions of these young planets with incredible clarity. Equally groundbreaking is Webb's ability to perform spectroscopy, the analysis of light to determine chemical compositions. When starlight passes through an exoplanet's atmosphere, it undergoes subtle changes, imprinting the signatures of various elements and molecules. By splitting the starlight, James Webb can identify these signatures, providing information about the exoplanet's atmospheric components. This technique could reveal essential clues, such as the presence of water vapor, methane, and other indicators of possible life. As Rigby noted, this is our first chance to understand in detail the atmospheres of exoplanets, particularly rocky planets similar to Earth. Since its launch, the Webb telescope has started unveiling the mysteries of thousands of distant worlds. For instance, it has observed WASP-107b, a scorching planet over 1,300 light-years away, where quartz crystals float in an atmosphere filled with vaporized rock rather than water. It has also examined GJ-1214b, known as the sauna planet, with a mass 8 times that of Earth and a steamy atmosphere. Even more puzzling are the rogue, Jupiter-sized planets drifting freely through the Orion Nebula, apparently disconnected from any parent stars. Each of these planets is unlike any we know in the solar system, presenting astronomers with both wonder and confusion. But that's just the tip of the celestial iceberg. Crucially, several hundred are relatively close to Earth, and these are now ripe for study with James Webb. One of them is Proxima Centauri b, our closest known exoplanet neighbor. Discovered in 2016, Proxima b quickly became a tantalizing focus for scientists due to its position within the so-called Goldilocks zone of its host star, Proxima Centauri. This habitable zone describes the ideal distance from a star where temperatures might allow for the presence of liquid water on a planet's surface, a fundamental ingredient for life as we know it. Since Proxima b is situated close enough to Proxima Centauri to receive potentially adequate warmth while orbiting within this zone, it has captured the attention of astronomers and astrobiologists eager to find a planetary candidate with conditions possibly conducive to life. Proxima b also stands out due to its similarities to Earth, with a mass just about 1.17 times that of our planet. This slight increase in mass may suggest an ability to hold an atmosphere, assuming one exists. Such an atmosphere could play a vital role in moderating temperatures and protecting the surface from harmful space radiation, raising exciting possibilities about whether Proxima b could have developed the necessary conditions to harbor life. Although Proxima Centauri, a red dwarf, is much smaller and cooler than our Sun, the close orbit of Proxima b compensates for this difference, potentially supplying the planet with enough warmth to sustain Earth-like conditions. Scientists speculate that Proxima b's temperatures might fall within ranges similar to those on Earth, a prospect that would be pivotal for sustaining water in a liquid state and perhaps fostering the development of life. For several years, these characteristics have fueled discussions about Proxima b's potential habitability. Could it have a thick, life-protecting atmosphere? Does it have bodies of liquid water, like oceans, lakes, or rivers? Is there any chance that life, either primitive or even more advanced, could have emerged there? Such questions about Proxima's landscape and biology began to deepen as new observations made by James Webb brought more surprises. Recent studies have shown that the Webb telescope has succeeded in obtaining remarkably clear and detailed images of Proxima b, capturing its atmospheric characteristics, surface temperature distributions, and more. This level of detail is unprecedented, giving scientists new insights into Proxima b's potential habitability. The telescope's observations even extended to the dark side of Proxima b, a region that remains in permanent shadow due to tidal locking. This phenomenon causes one side of the planet to continually face its star, while the other side is always turned away, experiencing eternal night. Such tidal locking raises questions about temperature differences and potential atmospheric circulation, which might affect Proxima b's overall environment. But what James Webb detected on Proxima b's night side has left scientists both intrigued and bewildered. The telescope picked up unusual emissions of light coming from the perpetually dark side, which did not align with natural processes such as volcanic activity or atmospheric auroras. These findings have led to the hypothesis that these light patterns might be artificial, potentially resembling city lights visible on Earth's night side when viewed from space. At first glance, this idea may seem improbable. After all, detecting something as specific as artificial lighting from an exoplanet situated over 4 light-years away would be an incredible feat. However, the telescope's sophisticated infrared sensors enable it to capture even faint emissions of light and energy across immense distances. The observed pattern on Proxima B's night side has shown an unexpected regularity, forming grid-like configurations, which would be highly unusual for any known natural phenomenon. If these grid-like patterns are indeed artificial in origin, they could represent evidence of city lights, marking one of the most significant revelations in the search for extraterrestrial life. Such a discovery would not only confirm the existence of intelligent life beyond Earth, but would also suggest that an advanced civilization lies relatively close, in cosmic terms, just beyond our solar system. This proximity, around 4.24 light-years away, would transform our understanding of humanity's place in the cosmos, challenging the long-held assumption that intelligent life might exist only at unfathomable distances or perhaps not at all. The knowledge that intelligent beings could live so close would alter our scientific frameworks, philosophical beliefs, and even our collective cultural identity. No longer would humanity be left pondering the hypothetical existence of extraterrestrial life. Rather, we would confront the reality of sharing our galactic neighborhood with another civilization. This revelation could lead us to ask not only what such life looks like or how advanced it might be, but also what its history, culture, and technologies might entail. Scientists would likely wonder if this civilization is aware of our presence on Earth. And if they do know about us, how might they view our species and our attempts to reach out into the stars? Such questions would fuel further research, inspiring an era of inquiry driven by a desire to understand our cosmic companions. The ripple effects of such a discovery would extend far beyond the sciences, impacting disciplines like philosophy, sociology, political science, and religion. It would force us to reconsider long-held assumptions about our uniqueness and our place in the grand narrative of life in the cosmos. The discovery would create a sense of both awe and vulnerability, as we grapple with the fact that we are no longer the sole intelligent beings in our corner of the universe. Not only that, one thing is for sure. The discovery of city lights on Proxima B would almost certainly ignite a global movement, one beyond anything humanity has ever known, to explore and, if possible, make contact with this extraterrestrial civilization. For centuries, humanity has been captivated by the question of whether we are alone in the cosmos, a mystery that has inspired both scientific endeavors and boundless fictional worlds. The tantalizing possibility of intelligent life so near to Earth would give rise to an unstoppable push to bridge that cosmic distance. It would become humanity's greatest challenge and purpose, with the dream of connecting to another civilization as. Today, even with all of our technological advancements, humanity's capacity to explore the far reaches of space remains limited. Our current capabilities would require decades, perhaps even centuries, to reach Proxima B, given that it lies 4.24 light-years away, or nearly 40 trillion kilometers. At present, the Voyager 1 spacecraft holds the record for the fastest human-made object, yet it would take more than 70,000 years to reach Proxima Centauri at its current speed. Such a time frame makes the notion of interstellar contact seem unfeasible. However, discovering artificial light on Proxima B would change everything. The urgency of bridging that distance could spur unprecedented advancements, driving the rapid development of revolutionary technologies once relegated. Some of the most exciting concepts that could become essential to this new age of exploration include faster-than-light travel and communication technologies. Ideas such as warp drives and wormholes, often dismissed as speculative or unrealistic, might soon become serious subjects of research, attracting not only scientists but also policymakers, private companies, and the broader public. With newfound purpose and funding, these theoretical technologies could move from the fringes into the mainstream of scientific inquiry. Humanity would no longer have the luxury of dismissing them, as impossible. The chance to communicate with another civilization would make these advancements urgent, perhaps even inevitable. One such concept, the warp drive, has long been a favorite in science fiction and has intrigued scientists for years. Made popular by franchises like Star Trek, a warp drive offers a way to travel faster than light by distorting space-time. The theory suggests that if a spacecraft could create a bubble around itself, contracting space in front of the ship while expanding it behind, the vessel could ride this wave of warped space, effectively moving at superluminal speeds without breaking the laws of physics. This idea is more than just fantasy. Researchers like NASA's Harold White have explored the feasibility of such a drive, concluding that it may not be entirely impossible. Though far from being realized, this theoretical framework gives us a glimpse into the future where interstellar travel might become achievable. If we detected artificial light on Proxima b, the warp drive could no longer remain merely a thought experiment. It would become a crucial goal of scientific research. The potential benefits are immense, a technology that would allow us to reach Proxima b in a fraction of the time otherwise required. Presently, even if we could somehow travel at the speed of light, it would take more than 4 years to reach Proxima b. However, with a warp drive, that journey could be reduced from millennia to mere years. This possibility would provide the first real hope of bridging the vast distances of space, making first contact a genuine possibility within a human lifetime. Another technology that would likely gain unprecedented focus is the concept of wormholes. In theory, wormholes are shortcuts through space-time that could connect distant points in the universe, making instantaneous travel possible. While wormholes have been a staple of science fiction, they also have roots in the physics of general relativity. Einstein and physicist Nathan Rosen first proposed these bridges in space-time, which later became known as Einstein-Rosen bridges, or wormholes. Currently, wormholes remain hypothetical, with no real-world examples or applications. However, if we were to confirm the presence of an advanced civilization on Proxima b, it would change our priorities. Researching wormholes would become imperative, fueled by the hope that such a civilization might have already mastered this technology. Learning how they achieved it could guide humanity toward breakthroughs in our understanding of physics, ultimately allowing us to create stable, traversable wormholes. The discovery of artificial light on Proxima b could also bring about a new era of space exploration centered around wormholes. If we could harness this technology, we might achieve near-instantaneous travel between Earth and Proxima b, transforming interstellar travel into a reality. For the first time, humanity would have the ability to journey beyond our solar system, changing our place in the cosmos forever. In addition to the push for faster-than-light travel, the discovery of artificial light on Proxima b would create an equally urgent need for faster-than-light communication. Since Proxima b is over 4 light-years away, sending a message through traditional radio waves would mean an 8-year round-trip delay. 4 years for the message to reach Proxima b, and another 4 for a response. This time lag would make any form of meaningful dialogue difficult, especially if we sought to establish diplomatic or collaborative ties with a distant civilization. One of the most promising avenues to overcome this barrier is quantum entanglement. Quantum entanglement links 2 particles in such a way that the state of one particle instantly affects the other, regardless of the distance between them. Though controversial, some researchers believe that quantum entanglement might allow for faster-than-light communication. If artificial light were discovered on Proxima b, it would put immense pressure on physicists to unlock the mysteries of quantum communication. This research could ultimately lead to the development of a reliable communication network that would enable instant messaging across vast distances. Such a system would revolutionize our interactions with extraterrestrial civilizations and potentially allow for seamless communication with future human colonies on other worlds. The discovery of artificial light on Proxima b would also have profound social and political effects, likely sparking an unprecedented level of international cooperation and innovation. Much like the space race of the 20th century, the quest to reach Proxima b would create a new era of scientific rivalry, but it would also foster collaborative efforts across borders. The stakes in reaching Proxima b would be astronomical. governments would recognize the magnitude of this endeavor, seeing it as an opportunity to place humanity on the universal stage. The possibility of encountering another intelligent civilization would spark a need for cohesion, as nations would understand the significance of presenting a unified front when approaching this alien society. Just as institutions like CERN and the International Space Station have brought together the world's brightest minds to tackle complex scientific questions, the effort to communicate with Proxima B's inhabitants would require similar, if not greater, collaborative energy. These alliances could take the form of multinational agencies and research partnerships dedicated to interstellar communication, each one drawing on the strengths and resources of its members to overcome the extraordinary challenges ahead. This mission would also demand entirely new research institutions, particularly those focused on faster-than-light travel and communication technologies. Imagine facilities dedicated solely to breaking the light-speed barrier, allowing messages to travel across light years in mere moments. These institutions would act as incubators of innovation, where scientists, engineers, and visionaries from across the globe come together to create methods of interstellar communication previously confined to the realm of science fiction. Such research could catalyze advancements in physics, energy production, and propulsion, leading to breakthroughs that would redefine humanity's reach in the cosmos. As governments and research bodies rally around the Proxima B mission, the private sector would see a surge of involvement and investment. Private companies, taking inspiration from trailblazers like SpaceX, would seize the opportunity to contribute to this monumental effort. The influence of SpaceX, which revolutionized the space industry by making rockets reusable, demonstrates how private ventures can propel humanity toward its most ambitious goals. Companies focusing on space exploration, biotechnology, and advanced materials science would witness immense growth as they contribute to humanity's quest to connect with another civilization. These private enterprises would likely compete to develop the most advanced technologies, from propulsion systems capable of traversing interstellar distances to biotechnological innovations aimed at sustaining human life on foreign worlds. This quest to reach Proxima B would transform the private sector into a powerhouse of space-focused industries, sparking new companies and markets around the challenges of interstellar exploration. This fusion of public and private sectors would be unprecedented. The commercial space industry would likely witness a renaissance, with corporations investing heavily in the development of spacecraft and research systems designed to bridge the gap between our solar system and Proxima B. Just as the internet spurred the creation of countless new businesses, the discovery of intelligent life would catalyze a new industry built around space technologies, interstellar communications, and planetary sciences. The Proxima B mission could inspire private companies to pioneer breakthroughs in energy storage, radiation protection, and habitat construction, all of which would be essential for sustainable deep space travel. Biotechnology firms would also find a crucial role in this mission. The hostile conditions of deep space demand enhanced human resilience, and research into gene editing, bioengineering, and even artificial life support mechanisms could become central to these efforts. Companies specializing in materials, science might focus on developing durable, lightweight materials capable of withstanding the harsh environments of space. Altogether, the quest for Proxima B would spark a renaissance in science and engineering, fostering collaboration between scientists and business leaders, and turning once futuristic technologies into feasible solutions. Beyond the technological and scientific realms, the discovery of city lights on Proxima B would spark a profound philosophical and ethical debate. Thinkers have long speculated about the existence of extraterrestrial life, but these speculations have always been theoretical. With concrete evidence of intelligent life, the ethical questions surrounding contact with another civilization would move to the forefront. One of the first ethical questions would be whether we should attempt to contact the civilization on Proxima B. While the discovery of city lights might indicate technological sophistication, we would have no way of knowing whether this civilization is friendly or hostile. Could making contact with them put humanity at risk? This question has sparked debates among scientists, philosophers, and even the public, highlighting both the potential for profound benefits and unprecedented risk. One of the main arguments in cautioning against extraterrestrials' contact comes from historical analogies. Encounters between technologically advanced civilizations and those less advanced have often resulted in the domination or even annihilation of the latter. Examples such as the arrival of European settlers in the Americas highlight the devastating impact on indigenous populations, whose societies and ways of life were forever altered or even destroyed. Such historical instances raise concerns that contact with extraterrestrials might follow a similar trajectory, with humanity potentially being at a disadvantage if the extraterrestrial civilization is more advanced. These historical analogies, while not definitive proof of future outcomes, suggest that the consequences of contact are unpredictable and may lean towards harmful. For instance, humans have struggled with ethical considerations and empathy towards their own kind, let alone beings from an entirely different star system. If extraterrestrials view humanity as insignificant or merely a curiosity, they may feel no ethical obligation to ensure our well-being. In addition, the technological gap between humanity and an extraterrestrial civilization capable of interstellar travel could be enormous. Even if such a civilization does not view humanity as a threat or obstacle, they may possess technology that inadvertently disrupts our systems. Advanced energy sources or communication systems could interfere with Earth's infrastructure, affecting everything from communication networks to the environment itself. If extraterrestrials possess highly advanced artificial intelligence or weaponry, they may not need to intentionally harm humanity. Their mere presence could trigger accidental catastrophes. Furthermore, humanity might have little chance to defend itself. Our technology, as advanced as it may seem, is primitive compared to what we might encounter. For example, if extraterrestrials use a form of propulsion that relies on manipulating space-time, the release of such technology in our vicinity could produce radiation or gravitational waves that harmfully impact Earth. The unknown nature of these potential technologies adds a layer of unpredictability to any encounter, leaving humanity vulnerable. Another layer of risk lies in the intentions of extraterrestrial civilizations. The range of extraterrestrials' motives is vast and unknowable. If extraterrestrial civilizations are as diverse as the species on Earth, their intentions could range from peaceful exploration to outright hostility. Some scientists, like Stephen Hawking, have warned that an advanced civilization might view humanity as we view bacteria or lesser species, insignificant and disposable. If extraterrestrials see resources on Earth that they need or find our presence bothersome, they may attempt to claim resources without regard for human welfare. Alternatively, the danger could stem not from hostility, but from indifference. A civilization with vastly different values and priorities may simply view Earth as an insignificant speck. They might not actively seek to harm us, but may engage in activities that inadvertently damage our planet. For example, if their technology requires large amounts of energy or materials, they might deplete resources on Earth or alter our environment in ways that are detrimental to human life. When humans explore new environments on Earth, they often bring with them bacteria, viruses, and other biological agents, sometimes resulting in unintended ecological consequences. Similarly, if extraterrestrial beings were to visit Earth, they could bring with them microbial life or biological agents that our immune systems have never encountered. Even if these extraterrestrial microbes are not inherently harmful, the possibility of contamination could have unforeseen impacts on our ecosystem and health. Additionally, humans could be equally vulnerable to extraterrestrial pathogens or viruses that operate on entirely different biological principles. These foreign microorganisms might interact with Earth's organisms, including humans, in unpredictable ways. The risks of biological contamination cannot be overlooked, as even minor microbial differences could have significant effects, potentially sparking new diseases or impacting food sources and animal populations. Beyond the physical and biological dangers, making contact with extraterrestrial civilizations could create profound psychological and societal challenges. Humanity's understanding of its place in the universe has been rooted in the idea that we are unique or even alone. Confirming the existence of a more advanced civilization could lead to existential crises, religious upheavals, and a destabilization of long-held beliefs. The implications of knowing that there are other, potentially superior beings in the universe could have profound consequences for individual and collective human identity. For some, this may result in awe and inspiration. For others, it could lead to feelings of inadequacy, fear, or hopelessness. Society could fracture under the weight of these new realities, especially if the extraterrestrial civilization appears to possess qualities that humanity cannot comprehend or match. Governments may react differently, some seeking to harness extraterrestrial knowledge for power, while others might prepare for potential conflicts. The disparities in reaction could create global tensions as nations compete to secure the attention or resources offered by extraterrestrials if available. Fear and uncertainty could also lead to a rise in extremist movements, with groups opposing extraterrestrial contact and others advocating for adaptation to new cosmic realities. It is also worth considering that extraterrestrials could bring knowledge and technology that advance human civilization in unprecedented ways. They could offer insights into medicine, energy, and technology that revolutionize life on Earth. However, this knowledge comes with risks. Any advanced technology could be weaponized or misused by humanity, creating new dangers. For instance, extraterrestrial technology related to energy or propulsion might enable us to build powerful weapons, leading to a new era of global threats or even interplanetary conflicts. The potential for misuse of extraterrestrial knowledge is not hypothetical. Throughout history, humans have often applied new technologies in destructive ways, such as nuclear power being used for both energy and weapons. Similarly, contact with extraterrestrials could lead to the dissemination of knowledge that, in the wrong hands, might harm humanity more than it benefits. Some theories propose that advanced civilizations avoid contact to protect themselves or younger civilizations like humanity from potential harm. Known as the zoo hypothesis, this idea posits that extraterrestrials intentionally avoid interfering with humanity's natural development, much like a researcher observing animals in a nature reserve. This hypothesis raises the unsettling possibility that contacting ETs might breach a protective boundary, exposing humanity to risks it is not prepared for. Alternatively, the silence could indicate that advanced civilizations understand the dangers of interaction and therefore limit contact to avoid existential threats. Breaking this silence could mean opening a Pandora's box of consequences we have yet to fully understand. The dark forest theory, popularized by science fiction writer Liu Cixin, proposes that civilizations avoid contact to prevent potential threats. In a vast, unknowable universe, each civilization might assume that others are hostile or competitive. Therefore, any signal sent could attract unwanted attention, leading to the annihilation of the sender.
Located just 4.24 light-years from Earth, Proxima b represents one of the most exciting prospects for finding life beyond our solar system. This exoplanet orbits within the habitable zone of its parent star, raising the tantalizing possibility that it could host conditions favorable for life. However, while the promise of Proxima b is immense, numerous challenges complicate our understanding of this distant world. But now, with the addition of the James Webb Space Telescope, a technological marvel that has pushed the boundaries of astronomical observation, we have just achieved a groundbreaking feat: the clearest image of Proxima b ever seen. And that could change everything we think we know about our closest exoplanet neighbor. Join us as we dig deep into the most intriguing revelations of Proxima b and what they might reveal about the potential for life beyond. Let's start with an overview of Proxima b. This world was discovered by astronomers using the radial velocity method, which detects the slight wobble of a star caused by the gravitational pull of an orbiting planet. This method provided strong evidence for the existence of a planet about 1.17 times the mass of Earth, orbiting Proxima Centauri every 11 days. This close proximity to its parent star places Proxima b within the so-called habitable zone, the region around a star where liquid water could exist on a planet's surface. Given that water is a key ingredient for life as we know it, the planet's location immediately sparked excitement about its potential to host life. Proxima B's discovery was especially significant because Proxima Centauri is the closest known star to the Sun, making its planetary system one of the most accessible in terms of future space exploration. This proximity has opened up possibilities for more detailed study and has led to bold proposals for missions to send probes to the Proxima system in the coming decades. Despite its closeness, Proxima B remains a deeply mysterious world. Classified as a red dwarf star, Proxima Centauri is significantly smaller and cooler than our Sun. And while red dwarfs are the most common type of star in the galaxy, they present unique challenges for planets that orbit them. One of the most intriguing aspects of Proxima B's mystery lies in the nature of its star. Proxima Centauri is known to be highly active, emitting frequent and intense stellar flares that could have profound effects on Proxima B. These flares, composed of radiation and charged particles, might strip away a planet's atmosphere over time, rendering it inhospitable. For Proxima B, which orbits just 0.05 astronomical units from its star, about 1/20th the distance between Earth and the Sun, the threat from such flares is a serious concern. The planet is likely tidally locked, meaning one side always faces the star while the other remains in perpetual darkness, creating extreme temperature differences. This leads to one of the major questions surrounding Proxima B. Can it sustain an atmosphere under such harsh stellar conditions? If Proxima B has lost its atmosphere, it would likely be a barren, lifeless world. However, some models suggest that it could retain a thick enough atmosphere to protect the surface from radiation. Alternatively, if Proxima B has a magnetic field similar to Earth's, it could shield the planet from these harmful effects. Determining whether Proxima B has an atmosphere and, if so, what it consists of, is one of the most pressing challenges for astronomers. Proxima B's location in the habitable zone suggests that liquid water might exist on its surface, but the conditions required for habitability are far more complex than simple proximity to a star. The intense stellar activity of Proxima Centauri, combined with the possibility of tidal locking, complicates the question of habitability. In the tidally locked scenario, one side of Proxima B would be bathed in constant daylight, while the other would be trapped in eternal night. The terminator line, the boundary between the day and night sides, might be a region where temperatures are moderate enough for water to exist in liquid form. This strip of twilight could potentially support life, but much depends on the planet's atmospheric dynamics. If the atmosphere is capable of redistributing heat from the day side to the night side, it might create a more temperate climate overall. However, if the atmosphere is thin or non-existent, the surface could be frozen on one side and scorched on the other. The composition of Proxima B's surface is another enigma. Is the planet rocky, like Earth, or is it covered in oceans or ice? Spectroscopic studies using powerful telescopes like the James Webb Space Telescope could eventually provide clues about the planet's composition, but as of now, scientists can only speculate. Some models suggest that Proxima B could have a significant amount of water, possibly as much as several Earth oceans, but this remains unconfirmed. Even if Proxima B has the right conditions for life, detecting signs of life from Earth presents significant challenges. Direct imaging of the planet is difficult due to its proximity to Proxima Centauri and the faintness of the light it reflects. Instead, astronomers rely on indirect methods, such as studying the planet's atmosphere for biosignatures, chemical markers like oxygen, methane, or other compounds that might indicate the presence of life. The James Webb Space Telescope plays a crucial role in these efforts. As the most powerful space observatory ever built, James Webb represents a leap forward in space exploration technology. Equipped with a massive 6.5-meter primary mirror and 4 sophisticated instruments, the telescope is capable of capturing the most distant and faint objects in the universe. Its infrared vision allows it to peer through cosmic dust and gas, revealing stars, galaxies, and planets with exceptional clarity. For Proxima b, James Webb's infrared capabilities are particularly crucial. Proxima Centauri is a red dwarf star, which emits most of its energy in the infrared spectrum. Proxima b, orbiting close to this star, is subject to these infrared emissions, making it an ideal candidate for Webb observations. Unlike previous telescopes that relied on visible light, James Webb can examine the heat signatures of Proxima b, providing new insights about this intriguing world. One of Webb's primary objectives in studying Proxima b is to analyze its atmosphere. Determining whether Proxima b has a thick, stable atmosphere is critical for understanding its potential to support life. Red dwarf stars like Proxima Centauri are notorious for emitting strong solar flares and ultraviolet radiation, which can strip a planet's atmosphere over time. If Proxima b has managed to hold on to its atmosphere, it would be an extraordinary discovery, indicating that planets around red dwarfs might be more resilient than previously thought. James Webb employs a technique known as transmission spectroscopy to investigate Proxima b's atmosphere. As the planet passes in front of its star, light from Proxima Centauri filters through the planet's atmosphere, allowing scientists to analyze the different wavelengths absorbed by various gases. By examining the light spectrum, James Webb can identify the presence of molecules like carbon dioxide, methane, and even water vapor, which are key indicators of habitability. The telescope's infrared capabilities are particularly advantageous for this task. Previous missions, such as the Hubble Space Telescope, were limited in their ability to detect atmospheric compositions due to their reliance on visible and ultraviolet light. James Webb, with its focus on infrared, can detect the thermal signatures of gases even in cooler atmospheres like that of Proxima b. The ultimate goal in studying exoplanets like Proxima b is to search for signs of life. While discovering an atmosphere would be a significant achievement, the detection of biosignatures, gases, or chemical compounds that suggest biological activity would be even more profound. James Webb is equipped to look for gases like oxygen, ozone, and methane, which could indicate the presence of life. Oxygen is a particularly strong biosignature, as it is typically produced by photosynthetic organisms. If the telescope detects oxygen in Proxima b's atmosphere, it would suggest that life, at least in some form, could exist on the planet. Methane is another important biosignature. While methane can be produced by geological processes, it is also a byproduct of biological activity on Earth. The simultaneous detection of methane and oxygen would provide compelling evidence for life. Moreover, Webb's ability to detect water vapor is critical for assessing Proxima b's habitability. Water is a fundamental requirement for life as we know it, and its presence in Proxima b's atmosphere or on its surface would increase the likelihood that the planet could support life. Webb's instruments are sensitive enough to detect even small amounts of water vapor, making it a powerful tool in the search for habitable worlds. While atmospheric composition is essential for determining Proxima b's habitability, understanding its surface conditions is equally important. The Webb telescope aims to provide insight into whether Proxima b's surface resembles that of Earth or if it is more hostile. Factors such as surface temperature, atmospheric pressure, and the presence of liquid water are all critical in assessing Proxima b's potential for hosting life. As told, Proxima b is tidally locked, meaning that one side of the planet always faces its star, while the other side is in perpetual darkness. This could lead to extreme temperature differences between the two hemispheres. The side facing Proxima Centauri may be scorching hot, while the dark side could be frigid. However, if Proxima b has a thick atmosphere, it could help distribute heat more evenly across the planet, potentially creating more stable conditions conducive to life. James Webb will measure the planet's heat signature using its mid-infrared instrument, or known as MIRI, which is capable of detecting thermal radiation emitted by Proxima b. By studying the planet's temperature distribution, James Webb can provide clues about the composition and thickness of its atmosphere, as well as the possibility of liquid water on the surface. Studying Proxima b is not only important for understanding this particular exoplanet, but also for gaining insight into the broader context of planetary systems around red dwarf stars. Red dwarfs make up about 70% of the stars in the Milky Way, and many of them are known to host planets. If James Webb finds that Proxima b is potentially habitable, it could suggest that habitable planets around red dwarfs are more common than previously thought. On the other hand, if Proxima b is found to be uninhabitable due to the harsh conditions imposed by its parent star, it would reinforce the idea that planets around red dwarfs face significant challenges in retaining their atmospheres. In either case, Webb's observations will provide valuable data that can be applied to other exoplanetary systems, helping scientists refine their models of planetary habitability. In short, the James Webb Space Telescope's exploration of Proxima b represents a new chapter in the study of exoplanets. With its advanced capabilities, James Webb is poised to provide unprecedented insight into the atmosphere, surface conditions, and potential for life on Proxima b. While many questions remain unanswered, the tantalizing possibility that it could harbor life or provide a secondary home for humanity has driven interest in developing the means to reach it. However, let's first accept that while 4 light-years may seem close compared to the vastness of space, it is an almost unimaginable distance in practical terms. Current human-made spacecraft, like the Voyager probes, travel at speeds of around 17 kilometers per second. At that speed, it would take over 70,000 years to reach Proxima b. Clearly, we need a radically new approach to interstellar travel. To make the journey within a human lifetime, the spacecraft must travel at a significant fraction of the speed of light. Achieving this will require technological breakthroughs in propulsion, energy generation, and spacecraft design, all of which are currently in their infancy. One of the major barriers to interstellar travel is the lack of a feasible propulsion system. Traditional rocket propulsion, which relies on chemical reactions, is insufficient for the vast distances involved in a journey to Proxima b. New propulsion systems will be needed, and several promising concepts have been proposed. 1. Nuclear propulsion. Nuclear propulsion, both fission and fusion-based, could offer a way to achieve higher speeds than chemical rockets. In a nuclear fission system, atoms of uranium or plutonium are split, releasing energy that could be used to propel a spacecraft. Theoretically, nuclear propulsion could achieve speeds up to 10% of the speed of light, making the trip to Proxima b in about 40 years. Fusion propulsion, which mimics the process that powers the sun, offers even greater potential. In a fusion reaction, atoms of hydrogen are fused together to create helium, releasing vast amounts of energy. While the technology to build a working fusion engine does not yet exist, it holds the promise of higher efficiency and faster speeds than fission, potentially reaching 20% of the speed of light. This would reduce the travel time to around 20 years. 2. Laser-powered light sails. Another innovative concept is the use of light sails powered by laser beams. This idea is central to the breakthrough Starshot project, an initiative proposed by billionaire Yuri Milner and supported by scientists such as Stephen Hawking. The project envisions tiny, lightweight spacecraft equipped with reflective sails that could be propelled by powerful lasers fired from Earth or from space-based stations. These laser-powered sails could, in theory, accelerate the spacecraft to around 20% of the speed of light, allowing them to reach Proxima b in just over 20 years. The key advantage of this system is that the spacecraft does not need to carry its own fuel, significantly reducing its mass. However, the engineering challenges are immense, including the need for an array of lasers powerful enough to propel the spacecraft and the difficulty of steering the light sail across vast distances. 3. Antimatter propulsion. Antimatter propulsion, while still highly speculative, offers the most efficient means of space travel known. When matter and antimatter collide, they annihilate each other, releasing 100% of their energy. In comparison, nuclear fission and fusion release only a tiny fraction of the energy locked within atoms. An antimatter-powered spacecraft could theoretically travel at speeds approaching the speed of light, making the trip to Proxima b in under a decade. However, producing and storing antimatter in the quantities needed for space travel is far beyond current capabilities. The energy required to create even a tiny amount of antimatter is astronomical, and the cost of producing just a few grams would bankrupt any nation. However, even if we solve the propulsion problem, there are enormous challenges associated with sending humans on such a long journey. The voyage to Proxima b would likely take decades, even with the most advanced propulsion systems. This raises several key concerns. 1. Human lifespan and aging. If a mission to Proxima b takes decades, we must address the problem of human aging and lifespan. One option is to send multiple generations of humans on a generation ship, where the original crew's descendants would complete the journey. However, this raises social and ethical questions about the nature of life on a spaceship, where entire generations would be born, live, and die without ever setting foot on Earth or the destination planet. Another possibility is cryogenic suspension, freezing the crew members for the duration of the journey and then reviving them upon arrival. While this technology is far from mature, research in cryopreservation is ongoing, particularly in the field of medicine. Achieving reliable and safe cryogenic sleep for humans would be a major breakthrough for interstellar travel. 2. Radiation and space environment. Space is a hostile environment. Beyond the protection of Earth's magnetic field, astronauts would be exposed to dangerous levels of cosmic radiation, which can cause cancer and other health issues. A journey to Proxima b would require advanced shielding technologies to protect the crew from this radiation. Additionally, the spacecraft would need to be completely self-sustaining, as resupply missions would be impossible. This means it would need to generate its own oxygen, food, and water for the duration of the trip. Closed-loop life support systems, which recycle waste into usable resources, will be essential. NASA is already developing such systems for long-term missions to Mars, but they would need to be scaled up and perfected for an interstellar journey. 3. Psychological and social issues. The isolation and confinement of space travel can have severe psychological effects. On a journey lasting decades, maintaining the mental health of the crew will be a significant challenge. Space travelers would be cut off from the rest of humanity, and the stress of living in close quarters with the same people for years could lead to interpersonal conflicts. Ensuring the well-being of the crew will require careful selection of personnel, comprehensive psychological support, and perhaps even virtual reality systems to simulate a more varied environment. Alternatively, robotic or artificial intelligence, also known as AI, crew members, could be used to minimize the psychological burden on human travelers. Given the dangers and challenges of sending humans to Proxima b, some have proposed that the first missions should be conducted by robotic probes. Advances in AI and robotics could allow for autonomous spacecraft capable of conducting scientific research, scouting the planet for potential habitability, and sending data back to Earth. A robotic mission could pave the way for human exploration, providing vital information about Proxima b's atmosphere, geology, and potential for life. These probes could also set up infrastructure, such as automated habitats or resource extraction systems that humans could later use when they arrive. Beyond the practical challenges of interstellar travel, there are more speculative ideas that could one day revolutionize our ability to traverse the stars. Warp drives and wormholes are concepts rooted in the theories of general relativity and quantum mechanics. While currently the stuff of science fiction, they represent potential shortcuts through space. Warp drives, first made famous by science fiction like Star Trek, propose a method of FTL for faster-than-light travel that doesn't violate the laws of physics. In 1994, theoretical physicist Miguel Alcubierre developed a model for a warp drive based on Einstein's equations. The Alcubierre drive proposes creating a bubble of space-time around a spaceship, contracting space-time in front of the ship while expanding it behind. This bubble would effectively move the spaceship faster than light without the craft itself exceeding the speed of light, a key requirement, since nothing can move faster than light within space-time according to Einstein's special relativity. The idea of the warp drive hinges on the concept of space-time manipulation. Space-time, according to Einstein's general theory of relativity, is malleable and can be stretched or contracted by mass and energy. In theory, by creating a region of contracted space in front of a spacecraft and an expanded region behind it, the craft could ride this wave and traverse vast distances at superluminal speeds without violating any physical laws. Essentially, the spacecraft would remain stationary within its bubble while the space around it moves. The Alcubierre drive is a speculative concept, and its practicality faces several monumental challenges. One issue is the enormous amounts of energy required. Early estimates suggested that the amount of energy needed to create a warp bubble would be equivalent to the mass energy of an entire planet. However, some later studies have refined these calculations, suggesting that the energy requirements might be reduced if we use exotic matter, a theoretical substance that has negative energy density. Though the warp drive remains theoretical, there have been advances in understanding the mathematics and physics behind it. In 2021, a group of researchers claimed to have found a new solution to the Alcubierre metric that significantly reduced the energy requirements, bringing the idea closer to feasibility. This research suggests that the warp drive might be achievable without violating known physical laws, but it would still require exotic materials and advanced technology far beyond our current capabilities. Another problem with the warp drive is how to generate and control the warp bubble. This would involve manipulating space-time itself, something that, as of now, we have no practical means to accomplish. Additionally, the presence of exotic matter, which has not yet been discovered, is crucial for maintaining the negative energy densities required for the warp bubble. Despite these challenges, the possibility of FTL travel using a warp drive is a tantalizing concept that continues to inspire researchers. Another promising concept for revolutionizing space travel is the idea of wormholes. A wormhole, also called an Einstein-Rosen bridge, is a hypothetical tunnel through space-time that connects two distant points. Wormholes would allow a spacecraft to travel enormous distances in a short amount of time by passing through a shortcut in space-time. Like warp drives, the idea of wormholes comes from Einstein's theory of general relativity. In 1935, Einstein and physicist Nathan Rosen used the equations of general relativity to propose the existence of bridges through space-time, wormholes. These wormholes could, theoretically, connect two distant locations in the universe, enabling instantaneous travel between them. The most well-known type of wormhole in theoretical physics is the traversable wormhole, first described by physicist Kip Thorne in the 1980s. A traversable wormhole would allow for safe passage from one end to the other, unlike many of the other solutions that lead to singularities or collapse too quickly to be useful. One of the main challenges in creating a wormhole is that it would require exotic matter with negative energy to keep it open. Like the warp drive, the existence of such exotic matter has not been confirmed. Without negative energy, a wormhole would collapse on itself before anything could pass through. This negative energy requirement is a significant hurdle, but it doesn't render the idea of wormholes impossible. In fact, quantum field theory allows for the existence of negative energy in small quantities, as seen in the Casimir effect, which raises the possibility that future advances in quantum physics could provide a way to stabilize wormholes. If wormholes can be created and stabilized, they could enable instantaneous travel between distant points in space. For example, a wormhole connecting our solar system with another galaxy would allow for immediate travel across vast distances that would otherwise take millions of years using conventional propulsion systems. Wormholes also raise intriguing possibilities for time travel. Since wormholes link 2 points in space-time, they could, in theory, be used to travel through time as well as space. This has led to some speculative theories about using wormholes as time machines, though the physics of time travel is even more speculative and fraught with paradoxes. In short, traveling to Proxima b is an extraordinary challenge, but it is not beyond the realm of possibility. With advancements in propulsion technology, human biology, and spacecraft design, the dream of interstellar travel could become a reality within the next few centuries. Although the technical and logistical obstacles are daunting, the desire to explore and expand beyond our solar system is a powerful motivator. As we stand on the threshold of becoming an interstellar species, Proxima b serves as both a destination and a symbol of humanity's enduring quest for knowledge and exploration. One day, perhaps, we will look back on this time as the moment we first began our journey to the stars. And what's notable, besides Proxima b, there are also other notable potential homes beyond Earth. And here is a quick look at the most promising exoplanets that scientists believe could harbor life or offer clues to the formation of planetary systems. The TRAPPIST-1 system, located 39 light-years away in the constellation Aquarius, has become a focal point in the search for habitable worlds. It consists of 7 rocky planets, 3 of which, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, are located in the star's habitable zone. What makes this system especially remarkable is that all 7 planets are roughly the size of Earth, and are in such close proximity to one another that an observer on one planet could likely see the others in the sky. The TRAPPIST-1 star is a red dwarf, much cooler and dimmer than our Sun, allowing the planets to orbit much closer to the star without experiencing extreme heat. This compact arrangement also means that studying the system is easier. Scientists can observe how the planets interact gravitationally, giving insights into their masses and compositions. TRAPPIST-1e, in particular, has emerged as a standout candidate for habitability. Its location in the middle of the habitable zone means it might have liquid water on its surface. Moreover, it is dense enough to suggest a rocky composition similar to Earth's. While the system's planets likely experience tidal locking, there's potential that atmospheric circulation could distribute heat, making parts of the planets temperate and potentially habitable. Elsewhere, LHS 1140b is also a top candidate. Discovered in 2017, LHS 1140b is a super-Earth orbiting a red dwarf star about 49 light-years from Earth. This rocky planet is about 1.4 times the size of Earth, but has 6 times our planet's mass, suggesting it is exceptionally dense. LHS 1140b orbits its star at just the right distance to lie within the habitable zone, making it a promising candidate for habitability. What sets LHS 1140b apart is its atmosphere. Scientists have detected a potentially thick atmosphere that may protect the planet from harmful radiation and maintain surface temperatures that could support liquid water. Given its mass and size, the planet's gravity could help it retain this atmosphere even under the bombardment of radiation from its star. This exoplanet's relatively short distance from Earth and the presence of a dense atmosphere make it a target for further exploration, particularly with instruments like James Webb, which can analyze its atmospheric composition in detail. If it harbors signs of water vapor or even biosignatures like oxygen, it could be one of the most exciting discoveries in exoplanet science. Kepler 452b, discovered by NASA's Kepler mission, has been dubbed Earth's cousin because of its size and location in the habitable zone of a Sun-like star. Located 1,400 light-years away, Kepler 452b is about 60% larger than Earth and orbits a G-type star similar to our Sun, although it is slightly older. The age of Kepler 452b's star, estimated to be 6 billion years, raises fascinating questions about the planet's evolutionary path. If Kepler 452b had conditions conducive to life in its past, it may have supported life for billions of years, giving it a significant evolutionary head start compared to Earth. However, its older star also means that it is likely to be experiencing a runaway greenhouse effect, where increasing temperatures eventually lead to the evaporation of water and the loss of habitable conditions. While Kepler 452b's distance from Earth makes it difficult to study in great detail, its Earth-like qualities and the fact that it orbits a Sun-like star make it a crucial point of reference in understanding planetary habitability. Future telescopes may be able to glean more information about this distant exoplanet. In addition, K2-18b is a fascinating super-Earth located 124 light-years away in the constellation Leo. What makes K2-18b so extraordinary is the detection of water vapor in its atmosphere, making it the first exoplanet in the habitable zone with confirmed water vapor. This discovery, made by the Hubble Space Telescope in 2019, immediately positioned K2-18b as one of the most promising candidates for further study. K2-18b is about 2.6 times the size of Earth and 8.6 times its mass, meaning it is likely a mini-Neptune with a thick atmosphere of hydrogen and helium. Despite its gaseous nature, the planet may have a rocky core and liquid water, a combination that intrigues scientists searching for signs of life. The presence of water vapor raises the possibility that liquid water exists on the planet's surface or in its atmosphere. Proxima c, another planet in the Proxima Centauri system, has also captured the attention of astronomers since its discovery in 2020. Unlike Proxima b, Proxima c orbits much farther from its parent star, making it an unlikely candidate for life as we know it. However, its large size, estimated to be about 6 times that of Earth, makes it a compelling object for study. Proxima c may have a thick atmosphere or even rings similar to those of Saturn. While it lies outside the habitable zone, studying this planet could provide valuable information about planetary formation and the dynamics of multi-planet systems. Additionally, Proxima c's proximity to Earth makes it an excellent candidate for future direct imaging missions. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.